long chapter. Okay, here's the test. Take a look over here. All right, there's no back side to it, but you're going to have to do all your work on a separate piece of paper. As you can see, well, first of all, I've redone the test. You can't see that, but I have. And I've added on a lot of stuff. Calorimetry problems, which we didn't have before. Internal energy problems, which we didn't have before. And a Hess's law problem, where you're doing it from the equations. And you have to reverse them and stuff. So there's a lot of stuff in here that wasn't in the previous test. All right, and the other tests used to be done in one period. You're going to definitely need more than a single period to do this. All right, I'll try to go over as many as I can. We only have about 17, 18 minutes.
Are they all problems? Or
yeah, well, the questions would be stuff like, is this reaction end or exothermic? Is it absorbing or releasing energy? Is it spontaneous or not? That kind of questions. Okay, so those kind of questions. Hello. Yeah. Could she go in about 15 minutes? She's right in the middle of something. Okay, thanks. Bye.
for me.
15 minutes. So we're done here. All right, let's try to go over as many as I can. I probably won't finish the actual problem for many of these, but I just want to show you how to set them all up. Let's start with, I never before that. Start with the first one, which is a simple delta H equals MC delta T problem. It's funny how, you've been doing these harder problems for so long, you kind of forget the easy ones. So let's see if you remembered how. Hopefully you will tomorrow as well. All I have to do with this one is delta H equals MC delta T. There's not a whole lot that can go wrong in this one. You know your mass is 20 grams. You know your specific heat of water. It doesn't tell you. How do you know it? You should know water. Yeah, you could either use one, if it doesn't ask you, it doesn't care, you could either use 1 calorie per gram degree Celsius, which just be easier, and that doesn't limit your significant figures. Or, if you have to go, if it wants it in joules, 4.184. And then your temperature is TF minus TI. It has to be that way to get you the right sign. Cools from this to that, so it's 40 minus 75, which is going to give you a negative value, which means that heat was released, right? Was given off. All right, whatever that answer is, what was that answer? Anybody get it?
Negative 2,930.
Anybody else get that? Great. We won't finish many of these. That's one we will. All right, let's go with the temperature change now. I want to convert Celsius to Fahrenheit. I mean, you can memorize one equation and then rearrange it. So, like, for example, what I gave you, I think, was Celsius equals 5/9 Fahrenheit minus 32. Is that right? That's what I gave you. So could you rearrange that? When you rearrange that, what did you get for Fahrenheit? Because that's what you're solving for here.
9/5 C plus 32.
9/5 C plus 32. And when you do the math, what do you get for Fahrenheit?
Negative 11.
Everybody else get negative 11? 11.2 or something like
Yeah,
that?
I got.
Well, it shouldn't be. It's only got two significant figures. It should only be two significant figures, so 11 would be the right answer. What did you do, by the way, to get it to Kelvin? You do not use the negative 11. You would have used the negative 24, right? And that would have given you 273 minus basically 24, right? So what would you have got?
249.
249. All right, next one.
We are racing through.
We are racing because we have a lot. We're only going to have like 11 of these to do. Everybody forgets about these. Enthalpy information equations, I have to be able to write the standard states of these guys that are I know I want to make C2H4 gas, all right? But I got to be able to create him from his standard states. So I got to look up carbon, solid, graphite, plus hydrogen, gas. You got to write those states down. That tells you which one they're in. Also, it tells you that that's where the delta H's are 0 for those two guys. I have to balance them with a 2 there and a 2 there. Sometimes you will need to use fractions. Don't be surprised by that in the test if I've got a guy that needs fractions. Need to do that a couple of the examples we did in either the notes or in the homework. I look up the delta H in the back of the book, and of course those two are 0, so I'm only really looking up this guy. What's his value from the back of the book?
It's 2.26.
Positive?
Yeah.
Are you sure?
Yes.
Are you positive? Get it? 2.26? All right. That's how many kilojoules there are per mole.
We don't have time for jokes.
Right, I know. If it's a positive value, all right, it is not over on this side. That means it was absorbed, so I have to put it somewhere over here. So you would probably rewrite that with 52.26 kilojoules over on that side of the equation. If it had been a negative value, you would have put it as a positive value over here. I like to keep the numbers positive. Fact is, you could put it still correct. Put it as a negative 52.26 on this side. That's silly to me to do that. I think I like to keep the energy positive and put it where it belongs. Is it being absorbed or is it being released? It makes more sense to me. All right. What's next? Next we had the heat capacity problem, right? Now for the heat capacity problem, there's going to be a difference between the two values you're going to get. You're going to be doing the same basic thing you did before. Delta H equals MC delta T. But this time, when you plug in your 70.0 grams and your specific heat of water, was I using joules here? Joules, yeah. 4.184 joules per gram degree Celsius. And TF minus TI raises temperature from 18 to 22, so 22 minus 18. When I get my answer, it is not going to be how much energy I supposedly put into this thing. All right, what's it going to be?
1,200.
1,200 only?
Yeah.
So the heat capacity, how much of that was wasted to the calorimeter?
800.
800. You would just simply subtract those two, and you get 2,000 minus 1,200, and you get 800. Okay. Show me the work for all that. I'm just doing these quickly, but that's a pretty easy problem. There is another one that I did not ask and could have on this test. So look up here. I didn't ask it this way, and you don't need to copy it down because this is the exact problem pretty much that you had from your homework. I'm sorry, from your notes. But I could have asked it this way. Okay, let's read this one together because this is a little going. I didn't have time to do every single kind of problem. I add two solutions together, all right, and it tells you the temperature change. It also tells you the density of the final solutions as well. How much heat was evolved. And it says using the calorimeter from the previous problem. So that previous calorimeter problem, once you get that 800 joules, what would you have to do with that 800 joules from the previous problem? Because that was not the, I told you how much energy was lost to it. I didn't say the last step. You have to divide by how many degrees Celsius that changed by, but basically by the delta T, correct? Did you do that in the previous problem? What did you get? 270? 207 joules per degree Celsius. That would tell you, now in this case, when you go to do this problem, you have to use that 207 joules per degree Celsius to do this kind of problem. The delta H, again, you should not be writing this down. It's the exact same problem you already have in your notes copied, so there's no reason to copy this down. You would take, well, in this case it was 24. I used different numbers in the previous one. So you take the delta H of the calorimeter, and that you simply get by multiplying whatever you got for your heat capacity. You said it was 207 in the previous problem, so it would be 207 joules per gram, times however many degrees Celsius this guy's changing. All right, that will give you a certain amount of delta H here. You would then do the regular problem. How much energy did you get for the two solutions reacting? This is kind of what we did when we did the Hess's Law lab. We took sodium hydroxide and hydrochloric acid, added them together, had to take into account the calorimeter as well as how much heat was given off by the solutions reacting together, and then you add the two together and you get your answer. So that's a possibility too. The calorimeter problem was done in the previous problem, okay? So that was done in this one here, all right? And I could ask you to do something else with that afterwards. All right, now let's get to the next one. That one wasn't even on the review. Here's one that was. Was this the next one on the review? 5?
Yeah.
All right. Now, obviously, this is one of those that will take me a very long time to do, and I'm not going to have time. But I will warn you about some of the mistakes you guys can make here. I've got to do it both ways. Delta G equals delta H minus T delta S is, of course, the hard way. You have to do it that way. I'm going to ask you to do it both ways in the test. You would solve for delta H first. You would use delta H from the back of the book. What are the 5 mistakes we're going to make there? All right, well, let's think about it. One is it's products minus reactants. So people will look up just reading left to right. That's a mistake. Another one, looking up the wrong states. Make sure you look at the right states of matter. Number 3, wrong column. What column am I looking in, right? Number 4, the coefficients. Don't forget to use the coefficients. And lastly, when you do go to do the actual products minus reactants, you've got to use brackets and distribute the stuff correctly as well. So the math alone is often a problem. So those are your mistakes you're going to make there. You would solve for delta H, delta H of the products minus delta H of the reactants, all right? And you'd get a number here. What is that number? Anybody do it and get it for the delta H?
Negative 571.6.
When you got what? Well, whatever. It doesn't matter. It's not important. If you show me the work for these, By the way, they should be both 0 for this one, so you should have only been looking up one number, which is the waters, right? Products. All right. Anyway, delta H, you get the delta S. This is another mistake I want to talk about. Your delta S is going to come out to be in joules per degree Celsius. All right. Now, what do you have to do with that? You're going to have to convert your joules. Who got a number for that one anyway, for the delta S?
Negative 326.38.
Anybody else get that? That one looks like everybody got negative 326.38. All right, if that's correct, I would have to convert joules on the bottom, kilojoules on top. 1 kilojoule contains 1,000 joules. Right. So that's going to make him 0.326. All right. So you're going to have a very small number for delta S, which is not a surprise. Yeah.
Do we have to show that conversion on the paper?
You don't have to show it, but you have to do it.
Okay.
All right. So delta G equals delta H minus T delta S. Your T is 298.15. That's your temperature. It's right in the back of the book or on that chart. All right. You're going to multiply that by your 0.32, because that's in Kelvin, 0.326 kilojoules per degree Celsius, per Kelvin. I said degree Celsius up here. It should have been Kelvin. All right. I'm doing this very fast, I know. All right. You'll get that answer, and that answer should be very close when you do the delta G to the delta G of the products minus the delta G of the reactants. You simply do that using the third column in that chart. Good. All right. What's next? Oh, this guy right here. We don't have a whole lot of time, but I'm going to set him up for you. Probably forgotten about him, but this is a first law problem. Okay, so it's heat lost plus heat gain equals 0. Remember this one? This one, it's all about algebra. All right, so you got to do the guy who's losing heat plus the guy who's gaining heat. You're going to have a lot of variables in it, because remember, the delta T is actually TF minus TI. And you're solving for TF. Okay, TF minus TI for this delta T. You're solving for the final temperature of this guy. There's a lot of math here. You've got to multiply these guys together, distribute, add like terms, all that stuff. It's all about the math. So here's why you must show me the equation, the numbers plugged in, so that if you get it to a certain point, and your only mistake is algebra, you're only going to lose a point or so. Whereas if you're using the wrong specific heat, and that is a mistake. If I'm adding iron, you can't use the specific heat of water in both cases. We did do that in some cases where I took hot water and cold water. It was the same specific heat. But here I'm taking iron and adding it to it. If you did this correctly, what did you get for your TF, by the way? Anybody get a chance to do that one?
20.9.
Anybody get 20.9? Anybody else? Yeah? Quite a few people? Looks like that's probably right. All right, again, if you get that to a certain spot, you're only going to lose points for the math, which is not going to be many. Bond energies. This is one of those we have to look up, right? You have to be careful. When you go to, I would recommend, like I told you, drawing these out. CH4, I would hope you all know looks like this. You've had enough organic to know that. Cl2 would be ClCl. CH3Cl, how would I draw him? I hope you would all draw that. All right, and why do we do all this? Because we have to find out how many bonds there are when we look on that chart in the book. How many bonds are there? Well, I'm going to have 4 times whatever I get for the CH bonds value. I'm going to have 1 CCl bond, ClCl bond. I'll have 3 CH bonds and 1 CCl bond, right? And then I'll have 1 HCl bond. All right, so you have to do that. You have to draw them out a lot of times to be able to do the energies, the bond energies correctly. All right? And then you multiply them out. And, of course, this guy, the biggest difference between him is delta H of the reaction equals, because we're dealing with the amount of energy it takes to break a bond, it's the delta H of the reactants minus the delta H of the products, the exact opposite of delta G, delta H, and delta S, using the back of the book, using the delta H of the formation. That's how much it takes energy to absorb the release. When they're formed, this is how much when they're broken up. All right, almost done. And we only have 3 minutes left. Number 8. Oh, I have to just basically show this one here. Here we go. Number 8. For the work. Remember, I told you there is a bonus question on here as well. And that will be involving PV work. But I didn't have really time to do any of those with you. I just talked about it a little bit yesterday. All right, so I'm taking...
Don't do it.
what would this guy be? All right, for work. Is work positive or negative in this case? What'd you think?
Negative.
Well, let's see what's happening here. I'm going to decide whether this guy is doing work, all right, on the system, whether energy is being given off to the system, or whether, like, for example, is it expanding, or is it going to contract? What do you think it's going to do based on it's going 2 gases to a liquid? It's going to expand.
To a gas.
It's 2 gases going to a liquid. It's going to contract. So work's being
You
done.
have G.
Oh, you're right. That's not a liquid, but it's still the correct answer because I have 3 moles of gas on this side, and how many moles on this side?
2.
So say either way, it is contracted. So it's still the correct answer. I thought that was an L there. All right. So if works, the system is work's being done on the system. What does that tell you? Look at your what did it say? All right. Okay, what about this guy right here? Combustion of propane. Now, that one is a common sense one, but you can also write it out if you wanted to see it. Common sense. The system's doing work. The system's giving off energy to do work. If I were to burn propane, don't you think you're going to be getting energy, giving energy, and doing work with that, right? That's what we do all the time. So that would be a common sense kind of thing. Now, these last two where you can't, I don't have time, obviously, to do it, and you were supposed to do them on your own, they are the ones, let me just say, okay, they're the ones where you have to really worry about this. Delta G equals delta H minus T delta S. You really have to worry about this. Okay, look, stop, don't pack up. Give me a second. You got 1 minute left here. You have possibilities positive and negative for a delta S. Now, which of those is going to always be spontaneous? This guy right here, third one down? Correct. Because negative delta H says he wants you to be spontaneous. Positive delta S, more entropy, more disorder, wants to be spontaneous. This guy's going to be always spontaneous. Where is it never spontaneous?
Either for the first 2.
No, only one.
Look at, they're the same.
Oh, right. Positive, negative, positive. Is that right?
Negative, what were you doing?
Which one did I do? Positive, negative.
One of them needs to be positive, positive. One of them needs to be negative.
Positive,
You should
positive.
have spent your day off sleeping too. You need
Is
it.
that right?
You need a negative.
So this one down here should be negative?
Yeah.
Whatever.
Yes.
I'm just making them up. All right, so which guy is never spontaneous?
Who knows? Yeah, we don't know.
Now you know.
The first one.
This guy right here, okay? And that one didn't really change anyway. So he had to never be spontaneous. Now here's the last question. All right, T is going to affect entropy. So the larger I make T in those other two, in the case of this guy, it's going to make him spontaneous. So when you solve for that T, when you rearrange and solve for T, and delta G is equal to 0, temperatures above that temperature you find will be spontaneous. If you rearrange and solve for T for this guy, and delta S is negative, then when you have temperatures below that. Finally, when it says boiling point, if we solve for the boiling point, you're just solving for T, right? You're just solving for T, and your boiling point will be like the water as a liquid going to water as a gas. All right, that was a lot to do.